Hi everyone, it's time for the last lecture of Chem 28. We're going to wrap up conjugation and we're going to begin this last video with the Diels Alder reaction. So we're in Key Concept Unit 5, the only document of Key Concept Unit 5, no part 1, no part 2, whatever. And we've already covered conjugated compounds in a previous video. So anyways, just want to get you situated. If you have your Key Concepts handout, start here and then scroll down to part 3, item 3, I should say, the Diels Alder. It's a cycloaddition reaction. And way back when we talked about mechanisms, and we said there's 3 categories of mechanisms. There are free radical mechanisms. Yep, and then most of our reactions are polar reactions. They have charges in their intermediates. And the third category were the pericyclic reaction, where all the bonds to be broken and all the bonds that were to be made all happen in one step. So it's a nice quick mechanism, but there's a lot going on. So let's talk about Diels Alder. Why is it showing up here? It's because it requires a conjugated diene. So I'm going to put the simplest one, 4 carbons with alternating double, single, double. You notice I didn't draw it in the normal zigzag structure. I'll talk about why in a minute. But to be proper, this is probably the most stable shape. And then the molecule can rotate about this middle single bond. Single bonds are free to rotate. So they can get both double bonds on one side. I'll just draw it like this. The other molecule you need, it's called the dienophile. I know, scientists making up new words again. So you know what a nucleophile is. That's a molecule that seeks a nucleus, seeks something positive. Why? Because it itself is negative or partially negative, so it's seeking a positive charge. There are other molecules we label electrophiles. Why? Because those molecules are seeking electrons, something negative. Well, we got this diene over here, so we need a reagent that wants to seek or attack the diene. Yep, that makes it a dienophile. Now, it's a weird word, but not scary. What the dienophile must contain is another pi bond between 2 carbons, for the most part. At least here, we're going to restrict ourselves to alkenes and alkynes. So I'll draw the simplest alkene, ethylene, right? So this molecule draws a skeletal structure. It looks like the number 11. No, it's 2 carbons double bonded together. And one molecule, the diene, plus a dienophile. We should label these. That's going to allow, those are the 2 reagents you need for a Diels Alder reaction. The product always contains a cyclohexene ring somewhere. Yep, a ring of 6 and a double bond somewhere. And the mechanism, we'll put it right here because it's all one step. Everything, all the bonds break and form simultaneously, and you need to know it. It's not too bad. Let's draw it here. This is how the mechanism is going to go. I'm going to redraw my, that's ugly. Let's try again. Draw my diene and my dienophile. And the way I remember the mechanism is I remember nature's, what I think of as nature's favorite functional group, benzene. It's her favorite. She likes the conjugation, alternating double, single, double, ring of 6. She likes it. And so I'm thinking, hey, maybe she's trying to bring these 2 molecules together in an attempt to make benzene. Well, she's going to fail. It's going to make cyclohexene. Kind of close, but not the same. But that's my motivation. At least maybe her motivation. I don't know. But by remembering this and comparing to what I have, you can see that if you just kind of snap these bonds together here and here, that would actually be benzene. And that helps me remember the mechanism. The mechanism is going to try and make bonds between these 2 carbons and these 2 carbons. And the way it works is you just kind of roll a pi bond over, kind of like when we're writing resonance structures. So remember, let's see, let's have an allylic carbocation here, and we had to draw the resonance structure. The pattern was take the pi bond and move it towards the reactive center, Okay, this is the reactive center of carbocation. It could be a radical. Later we'll see it could be an anion, a lone pair with negative charge. These three are all resonance stabilized, same pattern. Move the pi bond towards the reactive center. So it goes here. And then who lost the pi bond? This carbon did. So then the reactive center goes there. Positive charge goes there. Okay, so the main idea was this double bond, the pi bond rather, rolls over to the side. So to close up this bond, you pick. Do you want to take this pi bond and roll it over, or do you want to take this pi bond and roll it over? They both work. And I'll grab this one and say, hey, you two electrons, cinch up, connect these two carbons together. And as this bond forms, whoa, 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 this carbon's saying, hey, I already have 4 bonds. I have the 2 unwritten hydrogens and a double bond. I'm good. Too bad. Make room for a pi bond. Okay, the pi bond's coming in. That pushes on this pi bond to roll over and close up the bond between these 2 carbons. And then this carbon panics, say, wait, 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 I already have my 4 bonds. Where am I going to put this pi bond? Well, make room. Okay, this pi bond then has to roll over here. And that's it. 3 curved arrows, 1 step is the mechanism for the Diels Alder reaction. And then just follow the arrows. Well, what happened? You erase this double bond and put these 2 electrons here. And where there was a double bond, now it's just a single bond. Up here used to be a double bond. Well, not anymore. It's just a single bond now. The pi bond moved here. So vertically, there's now a double bond. This used to be a double bond down here. Well, the pi bond left, so now you just have a single bond here. And where are these pi electrons? Closing up the ring here. And then we have our cyclohexane ring. And that's the product. Some students pointed out to me that if you want to know where the double bond shows up in the ring, it shows up in between where the 2 dienes used to be. I thought, that's clever. So if you start in your diene, there's a pair of, what makes it a conjugated diene? Well, it goes double, single, double. So where the single bond is, that single bond will then be the double bond in the product of a Diels Alder reaction. Cool. Yeah, that's it. That's a Diels Alder reaction. A couple of more details. I guess I was lying. It's not it. But that's the main idea. And there's the mechanism. Sweet and short. Love it. Here's a little detail. It turns out that your dienophiles with electron withdrawing groups, meaning electronegative atoms, let me put this. Put it here. Go away. Nope, that's not showing up on your screen. Dienophiles with electron withdrawing groups work best. So we just did the Diels Alder reaction between this diene and this dienophile ethylene. Well, it turns out I lied to you. If you put it in the lab and you heat it up, it really doesn't work. You need a catalyst to make this work, high temperatures and pressure. But if you swap out this hydrogen for an aldehyde group, oxygen's electronegative, meaning it's going to create a polar covalent bond. The more electronegative oxygen pulls these pi electrons and the sigma electrons, both the double, the 2 bonds here, both of those are electrons. Bonds are made of electrons. They flow towards oxygen, making this carbon slightly positive, which will then attract these pi electrons over here, and they start flowing this way as well. And it turns out if this alkene, the dienophile, is short on electrons, it's more willing to go out and grab these pi electrons here and make the Diels Alder reaction go. At least that's my rationale. So if you put electron withdrawing groups with with nitrogen, more electronegative than carbon, or oxygen, definitely more electronegative than carbon, those are electron withdrawing groups. Okay, so all these work well. So instead of just having this normal looking one, why don't we take this molecule? Let's move my picture out of the way, put it over here. Yeah. Why don't we take this diene, and then let's use this compound, You got an alkene here, and then there's a carbon-oxygen double bond. So on an exam, you might be saying, oh, wait, which pi bond is going to react with the diene? The alkene does, the carbon-carbon double bond. The other one, the other pi bond is just along for the ride. So if you allow me to redraw, what is this? Ethyl propanoate, ethyl acrylate. In a skeletal drawing, it might look like that. The product is close up the ring. It's such a short mechanism. Why don't we show it? I'll draw it a little differently. Last time I started with this pi electron and moved it, that's counterclockwise, moved it this way. Why don't I go clockwise, starting with this one? Doesn't matter. Hey, pi bond, you close up the gap. This pi bond, you close up this gap. And that pi bond, you make the cyclohexenes double bond. So right here, these carbons all form a 6-membered ring, the cyclohexane. Wait, this single bond is then going to become a double bond. There's cyclohexene. This carbon is here. This carbon is here. And attached to this carbon is an ester group. So keep the ester group there. And then there's an oxygen. Finish off the ester with an ethyl group. There's your product. Let's do another one. Let's take methylpropanoate, propanoate, an alkyne, propine. Crazy word. That's the IUPAC system. And I'm gonna keep using butadiene, 1,3-butadiene. And now we got the triple bond here. And I'll not draw in the hydrogen because it's a skeletal drawing. And sure, I'm gonna zigzag it so I can count my carbons correctly. 2 carbons are here, then zigzag to the nester. And then maybe I'll start with this pi bond. Now, the alkyne has 2 pi bonds, but only 1 pi bond is needed to close up the ring. So 1 pi bond, the triple bond reacts, the other one does not. So you make your cyclohexane ring. This pi bond went across these 2 carbons. What used to be the triple bonded carbon is still here. Now the triple bonded carbons lost a pi bond, but the other pi bond's still there. So this line, if you will, you could put it outside the ring, still double bonded there, but I like putting it inside the ring. And then more detail, attached to this carbon is an ester group again. Right? So now you actually get cyclohexadiene, cyclohexane with 2 alkenes. This alkene came from the Diels Alder reaction. The other alkene came from the triple bond. Triple bonds have 2 pi bonds, but only 1 pi bond reacts in the Diels Alder reaction. Cool. What else do we need to know about Diels Alder? Move that over here. Okay, Diels Alder reaction is stereospecific. One outcome of stereospecificity is that if the dienophile is trans, then the cyclohexane ring will also have trans substituents. What are we talking about? Let's have a couple examples. Let's start with this, and then, I don't know, this time I'll have an aldehyde. But let's put another group out here. No, just an ethyl group. Okay, this has a single alkene. That's my dienophile. This is my diene. I probably should have labeled that one first because it's easier to spot. 2 alkenes, 2 enes, 2 alkenes is the diene. And then go ahead and close up the ring. This pi bond goes here. This pi bond goes there. 3 arrows, curved arrows, makes your cyclohexene ring. Where the diene used to have a single bond, that's where the double bond goes. This carbon and this carbon are these 2 carbons. This top carbon has an aldehyde group, so I'm going to draw it in there and I'll attach it in a second. This bottom carbon of the cyclohexene ring has an ethyl group. And then this is what we mean by stereospecific. Is this alkene cis or trans? This one is cis, right? The two identical hydrogens are on the same side, the left side of this double bond. That makes it cis. So if you start with the cis alkene, you get the cis product. That means the aldehyde and the ethyl group have to be on the same side of the ring. And you have to use wedge bonds, or you use dash bonds. And actually, it's this. Wow, this is the chiral molecule. So actually you get the pair of enantiomers. Is that right? Why does that look funny to me? This carbon has a part of the ring, aldehyde, other part that's different, and a hydrogen. Yeah, these are chirality centers. So you actually get both of these. These are a pair of enantiomers. On the exam, you would only have to draw one. Let's put this in parentheses. The most important feature I want you to know is if you start with a cis alkene, that's a dienophile, you make the cis product on the ring. Your pair of wedge bonds or your pair of dash bonds. What do you think happens if you have a trans dienophile? So let's draw it this way. Now the alkene is trans. Close up the ring. Do your Diels Alder reaction. Make your cyclohexene. Between where the dienophile had its, that's a diene. Between the two alkenes of the diene, that's where that double bond now goes. This arrow is actually telling you, put the double bond here. And then this carbon and that carbon of the dienophile are over here. And the aldehyde and the ethyl group are trans to each other on the alkene. They now must be trans on the ring. So you pick whether you want the wedge on top and the dash bond on the bottom, or vice versa. Yeah, you get both. And you get a pair of both enantiomers. There we go. You don't have to draw one of them on the exam for me. But make sure you add that. That's something you have to remember, right? So if I said, hey, predict the products, I probably wouldn't draw it this way. I'd probably give you the most common shape. You have to know that, hey, this plus this, you pick which product. And you have to remember to add the dash and wedge bonds. Is there one more detail? Oh, yes, there is. Okay, we kept talking about the dienophile. Electron withdrawing groups are better. The dienophile, if it's cis or trans products. What about the diene? Well, the diene has to get into the right shape in order to work. It has to be in the so-called Scis conformation. New words. So what's going on here? Well, if we have a normal alkene, and I put two hydrogens on the same side, this is the cis alkene. Cis means the identical groups are on the same side of the double bond or on the same side of the ring. Like right now, these two hydrogens are on the same side of this ring. We'll talk about that molecule in a second, but there's two meanings for cis, right? Same side of alkene, same side of the ring. That's kind of going on here. We got the double bonds on the same side of the single bond. That's when it can react. And when it's in this zigzag shape, the double bonds are on opposite sides of the single bond. It's not in the right shape. And it kind of looks trans. So that's when they add the S. The S stands for the single bond. So how are the double bonds oriented? How is the diene, the two enes, oriented? About the single bond? Well, about the single bond, they look cis. The so-called S-cis conformation, the S-cis shape. Get the double bonds on the same side so you can close up the ring. If it's in the S-trans, which is more stable, right? At least in this molecule, it's more stable because these groups are farther apart. There's a hydrogen here, there's a hydrogen here. They're starting to crowd each other out. This is less stable. But if it's in the more stable shape, it can't do Diels Alder, right? It can't close up the ring in a nice circle, hexagon. This is the wrong shape. Okay, so you need to know that. You have to, so if I draw, what is this, 1,3-butadiene as a zigzag, you'll have to remember, nope, the zigzag is the S-trans. I can't react in that shape. Bend it so it gets in this shape. This happens to be less stable, so it takes some time, some heat energy to make it work. Other molecules are can be locked into the S-cis, right? So about this single bond, the double bonds are always in the right shape. And so it turns out that right here is a diene, and its identical twin, another 1,3-cyclopentadiene molecule, can use one of its double bonds as a dienophile. So these 2 carbons and these 4 can do the Diels Alder to make a cyclohexene ring. This carbon is this carbon. It just kind of bends out of the way as the ring of 6 forms underneath it. And then these 3 carbons are down here, these 3 carbons. So I've never seen a bottle of 1,3-cyclopentadiene, but I've been told that the label might say this, but this is actually what's in the bottle, because these molecules react with themselves to form the Diels Alder product. And it turns out you then have to distill this. You have to heat it up to reverse the Diels Alder reaction and distill this. So if you want these individual molecules, that's how you have to do it. And then you can't let them sit together too long, because then they'll reform the Diels Alder product. Okay, so if they're locked into the S-cis, very reactive. If they're locked into the S-trans, completely unreactive, right? So can I do a Diels Alder reaction with this molecule? That's a conjugated diene. Got double, single, double. It's conjugated, it's a diene, but it's in the S-trans, and it's totally locked in that shape. I can't swing this double bond down to make it react. On the other hand, in a different molecule, what if we put the double bonds here and there? Okay, now it's actually locked into the S-cis conformation, and it is a very good reactive compound, a diene for Diels Alder. It's in the right shape. Okay, takes some work. You have to do some chemical reactions to make this happen. You can't, these are not in equilibrium. They don't just flip back and forth into those shapes. Those are different molecules. I think that's it for Diels Alder. Last topic, UV visible spectroscopy. Okay, so we have infrared spectroscopy. Molecules are going to absorb infrared light. That was our last unit. That was really useful for finding out which functional groups were present in a molecule. Well, you can also shine visible light and even ultraviolet light on molecules. And if a molecule has some conjugation, it might be possible for it to absorb in the visible or in the ultraviolet, sometimes both. Okay, so this is actually explaining how molecules can have color, is if the molecules have a lot of conjugated pi bonds, the molecules might have color. This is reminiscent of the electrons in transition metals. Remember your general chemistry? It's not on the test, but I'm actually substitute teaching for Gen Chem right now, so I actually did some of this. So let me show you what I remember. Where did I put it? Here it is. Okay, so with my other class in Chem 26, General Chemistry, we're looking at this nickel complex. Remember transition metal complexes? Okay, so nickel's a transition metal. This molecule has color. How do we explain it? Well, first let's get the charge of the nickel. That's some unknown X. And then you had to know that cyanide is Cn minus, has a -1 charge, and there's 4 ligands. Remember these ligands for transition metal complexes? So the charge on the nickel plus the total charge of the ligands has to equal the overall charge of -2. So we get x minus 4 equals -2. Add 4 to both sides, and x equals a +2. So this is a nickel +2 ion bonding, covalently bonding, coordinate covalent bonding to the ligands to make one big molecule that's a big anion, just a big ion. Anyways, what's the electron configuration of this nickel +2 cation? Well, it has the same electron configuration of argon. It would have the 4s2, and if you look on the periodic table, it's 3d8. That's for the nickel metal. But if you take away 2 electrons and make it a +2, the outermost electrons leave. They're higher up in the highest orbital. They're easier to remove. Highest shell, I should say. The 4th shell, easier to remove than the 3rd shell, which is closer, more tightly bound by the nucleus. We got 8 electrons here. You could draw the d electrons in the normal form like this. You're supposed to do spread out all 8 and then start pairing up. But in a transition metal complex, especially with these strong field ligands, and it's an octahedral complex. Is it octahedral? There's only 4 of them there. Probably should have put more groups on there. Yeah, let's put 2 water molecules in here or something. Let's make it octahedral, because that's the one I did before in Gen Chem. Let's put 2 iodides. Okay, now it has 6 ligands. It's an octahedral complex, right? It might look like we could put the iodides together, make them cis. And then the cyanides could be at the other points of the octahedron. Does this look familiar? Did I lose you yet? Sorry. Oh man, I feel compelled just to talk about this old stuff. This is not on the exam, by the way. Here's the bottom line. Why is it relevant? With these octahedral complexes, strong field ligands, you then change the orbital energy. You don't have all the d orbitals, the 3 d orbitals of the same energy level. 3 of these stay down low, and 2 of them move up high. And this energy gap is due to the identity of the transition metal, its charge, and the ligands. That'll change the energy gap between or among these d orbitals. And cyanide is a strong field ligand, so you get a large gap, meaning that the electrons will pair up on the bottom before they start filling up here. And with 8 electrons, you will get 2 electrons up here. Okay, hopefully that looked familiar. Why is it here? Because transition metals oftentimes have color. How does that come about? Well, if you have light come in with the exact amount of energy that matches the energy gap, these lower lying electrons can absorb the energy. Whoosh, the light ray is gone, but the energy from the light is used to excite this electron to make it bump up to the next higher orbital. The light got removed, and so if you have a large gap, well, maybe that was blue light. So if you start with white light, but some of the blue light gets removed, let's see, the primary colors are yellow, red, and blue. That's in white light. But if this energy gap is large, it takes a lot of energy. So which one has the highest energy? Blue wavelength has the most energy among yellow and red. And so that got absorbed. And so what used to be white light now comes out as a blend of red and yellow, which is orange. So this complex, I would predict to be an orange color. Then you have to go in the lab and find out if that's true. The main idea is start low, shine the light that matches the energy gap, then the light can be absorbed, and then the compound, if this light corresponds to visible light, then the compound will have color. Well, that was transition metals and different d orbitals having different energies. But we have our pi bonds. And we talked a little bit before in the previous video that if you create a pi bond, you're going to have a bonding molecular orbital and an antibonding orbital. So you're going to have one orbital up here and another one down here. This is your pi star, and this is your pi. And that's for a simple carbon-carbon double bond. And that's actually a huge gap. So to get an electron, so the pi bond, there's 2 electrons to be here. To get this electron to jump all the way up here, you need ultraviolet light, UV light, energy, high energy light to have enough energy to jump it all the way up to here. But if you start conjugating, you get more orbitals. And maybe these upper, no, the most extreme ones, maybe that has a significant gap, a large gap. Like if you want to move an electron from way down here up to here, you still need UV light. But now there's more orbitals. And so now this gap is smaller than this gap. And so you don't need as much high energy light. You can use light of lower energy, visible light. And so now these compounds with extended conjugation, lots of repeating double, single, double, single, double, single, creating more and more of these molecular orbitals. They're getting closer and closer together, getting smaller and smaller gaps. The gap energy corresponds to the energy of visible light. And so now your organic compounds can have color, just like the transition metals had color, but by a different mechanism, right? And the bottom line that I need you to know for the exam is that if you have more conjugation, you get more molecular orbitals, which allow for longer wavelengths of light, lower energy light. If that's a problem for you, just remember frequency times wavelength equals the speed of light. Frequency times wavelength equals a constant, speed of light. So high energy, let's see, energy is equal to h nu, Planck's constant, times frequency. So the faster it vibrates, this is slowly vibrating, low frequency, that means you have long wavelengths. But if it's fast, then you have short wavelengths, high frequency, lots of energy. That takes me some energy to move my hand, vibrated so fast back and forth. Yeah, that's how I remember it. High frequency is high energy, big gap you can climb, and corresponds to short wavelengths. These are opposites. High frequency would be a short wavelength. A low frequency would be a long wavelength. And that's what we're looking at. The pi bonds come in with a big gap, but if you conjugate them, get them repeating, you can create more molecular orbitals that then have a smaller gap, lower energy, longer wavelengths. And now you can get into the visible light spectrum. So here's some real data, maybe to solidify this fact. Scroll up a little bit more. There we go. We got 5 pi bonds here in this molecule called naphthalene. 5 pi bonds, right? They're all alternating with each other. Double, single, double, single, double, single, double, single, double. And it turns out it's this line right here. This is the absorption curve. It's absorbing light primarily around, what is that, 225. Visible light starts around 400 and goes to 700. This is where red, this is where blue is. So we're in the ultraviolet light, so we can't see this. So to us, naphthalene doesn't have any color. How many pi bonds are here in anthracene? There's 3 rings that are fused together. We got 1, 2, 3, 4, 5, 6, 7. 7 right? Everyone's conjugated. They're all alternating double, single, double. Huge number of molecular orbitals. Now the maximum wavelength of light, lambda max. Okay, so we're measuring the wavelength. Highest peak is your lambda max. Now it's shifted towards longer wavelengths, getting towards the visible. So more conjugation, longer wavelength. And we're measuring with the wavelength of greatest absorption, maximum absorption. Lambda max for naphthalene. Here's lambda max for anthracene. And actually getting some absorption here, but still in the ultraviolet. It's not until you get this molecule, which is tetracene. Lots of pi bonds, And then here's their lambda max. Still in the ultraviolet, but you can see the trend. The maximum wavelength, the wavelength of maximum absorption is moving towards longer wavelengths, towards the visible. And now there's other portion that's actually absorbing the blue light. Remember, it was the primary colors of yellow, red, and blue. So the blue light got taken out, leaving behind yellow and red. Yellow and red make orange. So that molecule, it should be colored orange. That molecule appears orange because it's absorbing the blue light. Last thing before we close out this video, conjugated molecules can make great sunscreens because they absorb UV light as well as visible light, but it's UV light. So how many pi bonds are conjugated here? Well, remember the ring with a circle in it represents benzene with 3 pi bonds. So here's a 4th one and a 5th one. There's 5 pi bonds conjugated here. How about this one? Well, you got 3 in this ring, right? It's benzene. Another 3 here, that's 6. Here's a 7th one. Here's the 8th one. And then the nitrile group is a triple bond. You only count one of the pi bonds. We'll talk about that next semester. Right now, remember that the pi bonds, the 2 pi bonds, one's in and out of the plane and one is in the plane. And to be conjugated, they all have to be lined up, p orbitals, overlapping p orbitals. So let's say that this pi bond is lying on the screen. This pi bond, the benzene rings are all on the screen. The triple bond will have 1 pi bond on the screen, lined up, can conjugate, yes, conjugated. The other pi bond might be sticking in and out of the screen. It's not lined up, they're not overlapping. So we got 3 pi bonds here in this ring, 3 here. This is a 7th, this is the 8th. Count one of those for 9 conjugated pi bonds. 9 pi bonds that are conjugated. How many over here? Just 4. Okay, fewer pi bonds means shorter wavelength, and that's going to help give you a wider range of UV protection, right? So oftentimes these, what are these called? Oh my goodness, need a break. Sunscreens, thank you, suntan lotions, sunscreens, they block out the UVA and the UVB, so different regions of the UV spectrum. And so this is going to absorb high energy, probably the UVA, I think. And then these with more conjugation absorb the longer wavelengths of UV. I think that's a UVB. And then together, these are sold as mixtures in these creams and sprays. You can get a lot of absorption in the broad wavelength, a whole bunch of UV light being absorbed, protecting you from ultraviolet light. Cool. All righty. See you in next semester in some more videos. Take care.